Desk of Ladyada.
Hey everybody, welcome to Desk of Ladyada. Beautiful Sunday here, doing some engineering.
Yeah,
looking
we're
at
back.
some rocks and prototypes. We're still unpacking because we unpack forever. So
It must be lat day because we're back.
we got all sorts of weird stuff. So Mr. Ladyada won't talk about the weird stuff.
Yeah, as I unpack, I'm just going to, if we happen to be filming, I'm just going to toss it over there and be like, show this off. So the first thing is, let's go to the overhead. Phil, go to the overhead.
You're in control of the overhead. Why are you asking me?
Yeah, I just thought I'd throw a wrench. So this is a rock. This is a thing that comes out of the universe like this. It grows, but it's like, what is it? What is it? What is it? You see this at like rock hobby shops and museum shops, and once in a while you'll see somewhere. But what is it? What is it? Well, everybody has a phone, and I've been trying to find an app that you just point your phone at the rock, and surely there's a way to do this. I was even thinking of building it, and then sure enough, something came wrong. It was called Rock Pick, and I don't know what all the different operating systems it's available for desktop, but it's a phone app. And this is you took a picture of that because we have a kid, and we have to like, she wants to know everything. So it's bismuth, and it's brittle metal with low melting point, known for its iridescent oxide surface. And then here you go, lady. If you move it off to the side there, you know, you can, yeah, there you go. So, you know, it took the picture with my phone, and then it looked it up and it did it. Now, there's one that it can't do, and I only got a chance to try it just for a brief second, and that was one of my favorite stones, the dinosaur stone. No, the TV stone, because it looks just like a crystal, a clear piece of glass, and then when you have to, it actually requires kind of the right thing to look at it, the right angle. So this is the TV stone, because if you were here, it'd be weird because we'd be like, how'd you get here? You beamed in. But it's a TV stone because it separates it from the text, and it's raised up. It kind of looks like water, how it diffracts water, but it's a similar thing. So it couldn't get this one because it can't see it. It can't see through it. But I'm going to try some other things, and I'm going to see if I can search in the database, or is it only if it sees a picture of it. Maybe I'll do the side. Okay. Okay, and the other thing is, you know, it's AI, everything's AI. So some of the hardware devices may or may not make it. And eBay had this AI agent thing that you could type what you're looking for. So I was looking for like a super cheap Rabbit. It's one of these like AI devices, basically like an Android phone, but it's like an AI thing. But I really like this this like Tokyo vending machine style packaging. And it would looks like it would just like come out of a vending machine, and this is a really neat wheel on the side, but just don't turn it on because I might film it or something, and then we're gonna take it apart, I think, more. But this is neat, right? It's like a little device. Look at this thing.
Little Android little speaker.
Yeah.
This was like the golden age of like, you could go to China and just be like, I want an Android phone, but with like an orange case, and they'd be like, yeah, sure, whatever. Yeah,
for too long, venture capitalists have turned China into the world's hardware manufacturing prompt.
Yeah.
I would like an orange box with a rabbit, you know.
And so like this little like rotating.
Yeah, and like, you know, I like all these gadgets and stuff like that, but I know I am not mass market. Like if I really like a device, it's probably not going to make it past like 2,000 customers. So anyways, I like this. I want to learn its secrets. Okay. And so do you.
Yeah. All
right, Ladyada. We got shows and more this week. Let's kick it off with some Desk of You. What you got going on this week?
Okay. So back to the computer. This is the Wikipedia of the Rabbit.
Oh, yeah?
On my computer.
Yeah, I couldn't tell if they're still in business or not, but whatever.
It's a little unclear. Other people can figure it out. Okay, so I worked on a couple things. So I'm trying to get stuff back into the shop. And so this week, we did a little bit better on getting stuff in, because like this was like the only product 2 weeks ago. So last week we got the Sparkle Motion stick in, and we still have some of the enclosure. The SEN6x breakout, which I don't know why it didn't make it into the shop. I have to yell at them. I think they were like got out of practice for like 6 weeks or 4 weeks of not so much stuff.
That's one of the unintended consequences of Tariff Town.
I know.
Your population forgets how to
they just like
how to do things with regular non-tariff stuff, and then we're just like, what do we do?
Yeah.
What do we do?
Anyways,
what was it like before?
This will be in on Monday. I'll have to like start to remind them like, hey, like new products. Yep. Catalog team.
We'll get back on it.
Yeah, it's fine. But this will be in shortly. People are wondering why. I don't know why it's not in. I think they just forgot to do it. Okay, and then so then next week we're going to get the OPT 4048, which you can go on the overhead again, and I'll show it off. So this was a little, I was just trying to get some like simple sensor breakouts in because I'm trying to like kind of get the pathway of getting products in, and some are more complicated, some are simpler. So this one, it's like I knew that it was working. I just had to write the driver for it. So I co-wrote it with Claude, and it wasn't too bad. It's actually not such a complicated sensor. It's just actually there's the data sheet has typos in it, and that really, really confused Claude because it was like there's a part where it says here's how to calculate the CRC, but they made a typo. And like what's weird is that they even like TI is like, oh yeah, we made a typo, and I'm like, then why don't you have a new data sheet without a typo? Because they have the wrong bits selected in the CRC, and it doesn't make any sense. And then they tell there's no errata even. It's like you have to just go to another page and they tell you how to do it. Very stupid. Anyways.
Well, when folks ask like, why do we need some of these tools? This is one reason, because the human capital that's lost trying to figure this out, it's years.
Yeah. Well, the problem is actually like the thing is about Claude is it doesn't have doubt. Like it kind of trusts whatever it's given. It's like, oh, you humans must be correct.
I thought you said gout.
So
because it doesn't have feet. I thought you said gout. I'm just like, it doesn't have feet.
No, it has doubt. So it's like when I look at a data
it's a people pleaser.
Yeah, I mean, it just trusts whatever.
Yeah.
Whatever. So
it'll lie to you.
All right, let's go.
Yeah.
So what I did is I wrote a driver for this, and then I wanted to for the sensor design something like this where I could have the color, because it's a color sensor. It gives you the CIX and CIY data, but that data is like it's not that human usable. So like if you look at the output of Arduino, it's like the color temperature, okay, you can kind of tell it's like 3000 is a little warm, a little neutral. The lux, you can figure out, is it bright or not? But the CIE color temperature, it's like a plot within this chromaticity diagram that like, why would you know about? So I thought of like, okay, I could use processing or JavaScript to write an app to plot the data on it. But it's been like 15 years since I wrote any JavaScript. And so fortunately the app wasn't I couldn't make it responsive to 720p. So that's the only downside is like, I don't know enough JavaScript to do that. But I did manage to use Claude to write this JavaScript page that's hosted on GitHub. So it's a GitHub page, and it's under the repo, and it's in like a folder called Web Serial. And when you connect to it, oh wait, I have it open here. Hold on. It will plot the XY data. You can see like down here, it reads the data from the serial port, parses it, and then displays it on this SVG, which was, I'm in the way, so let me hold it up here. So yeah, this makes sense. It's kind of like I got like kind of warm lights in here. And it's not like sunlight. If I point out the window, it would be a little bit cooler. And then one of the tricks I did to figure out like, is it actually working is if you point it at the screen, if I put it over like the pink area, it turns pink, and then I move it over to like the blue area and it blue because it's reading the light from the monitor. Sometimes the monitor is not great for greens, and you can even see that like this whole area looks kind of all the same color. It's just not, this monitor is not awesome for green. Like our eyes are better at green detection than what our monitors can display. That's just like something that I don't have to deal with because I don't do like print or color matching and stuff, but that's why we have like Pantone papers on paper. So what's nice is that like this, only took like 30 minutes to do as a JavaScript app with Claude, which would have been, really challenging to do if like I had to sit down and do it, probably would or if I had assigned someone, it would have taken a week. I probably actually just wouldn't have done it. I'd been like, hey, just here's how you plot it. Good luck. So it's kind of neat to see. I've never written JavaScript with an AI tool, and it's also the first time where I'm writing code. It's not like I couldn't read it, but I can't. It's not like I'm architecting it. I was really like, I want this app to look like this. Can you just like figure it out? And it took a couple back and forths to get what I wanted, but it came out quite nice in the end. So I might do this for more sensor breakouts that we have because there's a lot of times where it's like, well, I can have the data display on the serial port, but there's no easy way to plot it or graph it because the Arduino plotter is really designed to like plot one XY. So if I wanted like two XY graphs, like you can't do that on the Arduino plotter that I know of. I've never, it's only been just like one graph. And so if one value is in, microvolts and the other is in milliamps, you're not going to be able to see both images because you can't do dual Y ranging plots. Okay, so that's one thing. And then, so then we did a couple breakout designs. So the big breakout design I did this week, which I kind of sat down like all Friday to do, is the BQ25798. So this is a pretty beefy battery charger, and it can charge 1 to 4S batteries. So there's a little switch down here where you can select which size battery you want, and like by default it's 4S, and then if you have or maybe it's 1, I don't remember, but like you switch all the switches on and you can switch which one you want, and then before you plug in your battery, just measure the output voltage to make sure it's like, okay, that's correct, but like before you connect your battery, and then don't mess with it afterwards. And then there's a load output as well, which will give you either VBAT or the output of the buck boost converter. This is the buck boost converter. The inductor is not too chunky, actually. It was only like 7 by 7 millimeters, even though this is a 7 by 6 millimeters. It's a pretty beefy buck boost, but what's kind of neat is that you can power it from DC. So I've got like a DC terminal block in here. A terminal block, a DC jack. There's P-mid. That's like this weird output where you can have it like buck boost out if it's not being powered, but like you have to have no power in. So it's I made a breakout for it, and like I don't think anyone's gonna use it. Or you can have USB, and there's 2 inputs allowed, and so you actually need that if you're doing. So this is one input. This is the DC input, and you can have either the 2.1 millimeter DC jack or terminal block. And then you have these back-to-back diodes, and these turn into an ideal. This is basically DIY ideal diode. If you guys remember from last week and the week before, I think we were talking about ideal diodes for solar. They actually kind of designed it in a nice way where you can. They're like, as long as you follow the schematic, you can turn on and off either input. You can like disable or enable each input programmatically, while also measuring the voltage, and you don't have a big voltage drop. And so these both feed into VBus, but these they have to be activated in order to turn on. So they're very low forward voltage drop, and that's good because solar panels, you want to lose as little as possible in the voltage. And then this chip does the buck boost conversion to get from whatever power is in DC, USB, solar, whatever, into the battery voltage. And so the DC input can be below or above, or like around the same value, and it will just automatically switch between whichever mode in order to get you the correct voltage output to charge the battery that you desire, which is kind of neat. Like, it's rare to see something that can handle both. Like traditionally we use linear chargers because you give it 5 volts and then it will charge a battery up to 4.2 volts. And it's like, there's not, it's inexpensive. It's like 20 cents to make a charger, maybe even less. You lose a little bit of power, but who cares because you're plugged into the wall. So it's like, it doesn't matter if you're losing 20% because the amount of power is very little. With solar, you really want to have the most efficiency. And then the other nice thing is it has true MPPT tracking, so max power point tracking. So I guess it's tracking, but whatever. It's like an ATM machine tracking PowerPoint tracker. So for solar panels, it will do this algorithm where it like finds the max power point by kind of jittering around the current set point. And now you're also doing some math. And as the day goes and the sun moves and the clouds move over and it like some days it's cloudier and some days it's warmer and some days it's colder, all that stuff affects the set point. So, and especially with the buck boost, it's not obvious where that max point is because there's also the inefficiencies of the buck boost converter itself. So usually buck is a little bit more efficient than boost. And so you might have a higher set point, even though like you might think you get more wattage from a lower set point, maybe the higher set point actually is a little better because then you can buck it down. And then with the overall efficiency of the whole system, that gets you the most power. It's only for lithium batteries, which is a little bit of a downer. I think that you can set the output voltage, but like you're still kind of, you know, if you don't have I squared C, then you're kind of dependent on what these switches say, because there's this like mechanical setting and then there's the programmatic setting. So it's a bummer because I know people are going to immediately ask like, well, I want these for, you know, lithium, like cobalt, whatever, the other type of battery, lithium phosphate battery or lead acid. And the answer is no, this doesn't do lead acid or lithium phosphate, but Bug TI, they can easily tweak the chip to do it, right? It's not like too hard for them to tweak it to say, okay, now it supports lithium phosphate cells. But I think, which is actually a little bit odd because you'd think for safety, a lot of devices that would have solar, like if it's going to be outside, maybe you want to make sure that it also doesn't catch on fire. But you can't really beat the prices on lithium ion. And then we have full breakouts. And then there's I squared C. There's a Stemma connector here. This is an I squared C controlled thing. You can set the hardware current limit and the number of voltage cells with like this trim pot and with the switches. But then for like the detailed configuration, also you can measure the voltages, measure the current being used, the charge rate, to like the percentage of the battery, like et cetera. You can measure the thermistor. You can do so much stuff. That happens over I squared C. So if you want to do the more advanced, it can run on standalone mode, but it's like if you want to do, I think if you want to activate max power point, you do have to have I squared C on. So it's not fully autonomous. That's okay. So I got a breakout for this going. It just took a while because there's like a lot of little pieces to get going. And especially, you know, I had to like spec out all the, these back-to-back diodes, these back-to-back FETs, the Zener diode, just make sure it matched the schematics. Just like picking through the schematic and making sure I got all the little things that they wanted. And then, you know, it's like I'm not running a valve board, I'm running a dev board. Okay, so that's done. I made this little breakout because I was actually kind of getting tired of like plugging in little cables into a Stemma QT. So this has like a socket, like 2x3 socket, plugs into a Raspberry Pi, just gives you a Stemma QT connector. That's it. And then it has like pull-ups and stuff. Because even though there's pull-ups on the Raspberry Pi, not every single board computer has them. And so I wanted to add them like 10K pull-ups, regulator, LED. So I had a little breakout. I just like threw out because I was getting annoyed. And then I made a little breakout, kind of standard, you know, 1 inch by 0.7 inch breakout for the Vemel 6046. So what I really like about this sensor, it's a very high lux sensor. And we had a couple people asking for high lux sensors. And I was like, yeah, we don't have anything that goes really high lux. Although, to be honest, the sunlight, I don't know where you'd be where the sunlight gets so bright that it's 180 kilolux. But I don't know, maybe
Mercury.
Yeah, maybe you're on another planet or something. So that got done. And then how are we doing on time?
Well, you're up to the 18-minute mark, so you can move on to Great Search, or you can hang out and talk about the sun as much as you want. Yeah. So then the last breakout I did, because I did the INA 228 and then I did the INA 237, and then I had somebody say, hey, can you do something that has more than 10 amp of current? And I was like, yeah, I guess like I have done enough like LED projects where it's like I actually have gone into like the 10, 20 amp size. It's like you get like really big LED screens. So this is a power monitor that can handle up to 30 amps. And it does this actually, apparently there's like, it's like a magnetic sensor. There's no like sense resistor because like no sense resistor is going to, I mean, you could do it, but it's like, it's going to be hard to have a sense resistor that can handle that much current. So this is, actually the milling line is not appearing here. Let me show it. Okay, there's a milling line. I don't know if it's going to come out on the PCB, but there's it is actually something that you can handle 120 volts AC. Although I'm not going to tell people to use it. I'm going to say like, look, max out like 60 or so volts. But the big thing is it can do a lot of current, and it's I squared C output. This is the AC 3788 breakout. I'll say that 800. Paloola has a really nice breakout too. Theirs is like really intense. It has like kind of everything, including like fully isolated I squared C and like a regulator. It's meant to like kind of do as power isolator. This isn't designed for that kind of work. Like I'm not assuming that you're going to have. Obviously, this part is isolated, but it's there's no electrical isolation on the I squared C
I don't think you need it because this part is electrically isolated. So if you want to have some separate power supply that's also isolated from the power, like you would have to craft that yourself. This is just to make it easy to measure from, like, for example, LEDs or like motors or something where that the power supply has a shared, actually doesn't need a shared ground. It doesn't need a shared ground, but your system for measuring your current doesn't need to have isolated power or ground from the rest of your electronics system, which again, I don't know, maybe they found a need for it. I don't. Cut isolation layer here, and then these big ass terminal blocks. And you're probably wondering, like, oh my God, why are these terminal blocks so huge? That's because I actually need to get barrier blocks that can handle 30 amps. And speaking of barrier blocks that are 30 amps, let's go to the Great Search and let's find them.
Oh boy.
Where in the world is that part I need? The Great Search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit every single week. Ladyada looks for things on digikey.com. We call this the Great Search. Ladyada, what do you look for this week?
Okay, for this breakout, for the ACS37800, which is a 30 amp AC/DC power monitoring chip. So this chip can monitor very high currents at fairly high voltages as well, 120 volts easily. And it's isolated from the rest of the electrical system. So good for measuring, like, I was mentioning, like lots of LEDs, like really big LED displays, stuff with motors, stuff with lots of solenoids, anything where it's like, before you know it, you're like dealing with 10, 15, 20 amps. We have some chips that can measure current at about 10 amps, but you need to use a sense resistor. This is actually uses like a totally electrically isolated magnetic sensor system. So the only thing about this chip is, in order to get the power into the breakout board, I need to have some way for people to plug or connect their power. And let's go to, what I wanted was a terminal block that could handle high current, 30 amps. But then as I was thinking about it, I was like, well, if I'm dealing with stuff like LED panels, like the Hub 75 style panels, I usually don't have bare wires. I have actually everything on spade connectors. And so I wanted to have a terminal block that was spaced far enough apart that you could use spade or lug connectors, which is what you're going to have for like very high current setups where you don't want these loose wires that are carrying 30 amps. You want something that's mechanically very sturdy. And so instead of using just terminal blocks, I decided to use barrier block terminal blocks. So they're very similar to terminal blocks, right? Where you would plug a raw wire in. These can handle raw wires, but what's really great about them is that they have literally a barrier in between. And so you can have the wire wrapped around, and you don't have to worry about it coming out, but also you can put spades and lugs in, and then you loosen it. You put raw wire in just fine, but you can also put things that are like double pronged or have like a circular lug at the end. So let's look for, I need 3 pins because I need the power, load, and power minus, because you need both power wires, and you also need the load output wire. So 3 pin outputs, barrier, and it has to handle up to 30 amps. So let's look for active, 3 pin. I want 3 entries, 1 row. And current rating, 30 amps or above. So we'll just, I don't think I'm going to do something with 600 amps because it's probably going to be expensive, but I might as well, I'll get the little dash as well. I want something normally stocking. And I'm going to ignore the marketplace products for now. I'm just going to look at stuff that's stocked at Adafruit, at DigiKey. A lot of good options. So again, these are all really nice little barrier blocks. I like these. It's a very common thing. Some of them have like 3 sides. Some have 2 sides. I kind of like the 3-sided version. I don't know if I can select. Yeah, they're all gonna, they have 3-wall or 2-wall. So let's go for the 3-wall. Kind of this 3-wall style. Tri barrier. Because I don't want the wire to stick out and then accidentally touch the circuit. And all these have like 300, 600 amps. Some of them have 50, 45. Whatever. All looking really good. And then the next thing is, there was the pitch. So to make it so that it fits onto this board, let's go into millimeter. I don't know what, for this, I just picked something that was in my library, but let's measure the pitch. So this is 9.5. So something like 9.5 isn't too bad. I have enough, I had enough space for the circuits. I can go a little bit bigger, like if I need to go 10, but 9.5 is pretty good. So let's see what's available. 9.5, 9.53. I think I'm not going to go to 11. That also cuts out the 45 and 50. So obviously if I was picking, there's a version of this chip that can do 90 amps. Obviously I would have to go with a totally different connector because, I would need to pick something that's so big it can handle 90 amps, but 30 amps is perfectly fine. Only 3 options, so that's kind of good. One isn't even in stock right now. I can do this one or this one. This one's a little bit inexpensive. It's also Amphenol, which I've used a lot. They're really trustworthy. These are basically equivalent. This one's my pick. This is the YK44103030G. Let's see if we can get the 90% all rendering. Yeah. So you can see there's the tri-connect, and then there's little captive plates. It's kind of nice. And then, it's not too bad. All you do is you just have the pins solder in. You just put lots of solder in to mechanically connect it, and you're good to go. So that's why when I made this package, you see I made gigantic pads, big rings for lots of solder, lots of mechanical strength and electrical connectivity. So that's my pick for this week's Great Search from Amphenol.
Okie dokie.
Any tech.
That's a great search.
Where in the world is that part I need? The Great Search with DigiKey.
That's our show.
Yep.
Let's do much work, go outside.
Okay.
Let's do it.
Bye.
Bye, everybody.